All right, XY axis. All right, so the first one, let's say we had y equals x squared plus 4x minus 4. No, plus 4. Let's do plus 4. And then let's do x squared minus 4 down below. Okay? So a few things about this problem that you would want to do is you would want to break it into factored form. And factored form is going to tell you a few things. Being that I have these the exact same, this means that we're going to have a hole in our graph. Okay, a hole is different than an asymptote because your graph draws along it, jumps over the hole, and keeps going. So it's pretty much the same slope along it. So at -2, and how I get -2 is I would just set either of those binomials equal to 0. We would get that. And then if I plug -2 in, I get -2 plus 2 is 0. 0 over -4. So at -2, 0, I have a hole. Is that okay so far? Being originally my degree on top and my degree on bottom are the exact same, I take the lead coefficients, and this gives me my horizontal asymptote. And our horizontal asymptote will be at y equals 1. And then I have a vertical asymptote in here as well. The vertical asymptote is related to that, which is at x equals 2. Just setting to get then that equal to 0. Okay, does everyone feel comfortable that the hole is down here in the lower quadrant? Okay, so that means that when I make my graph kind of does something like this and jumps over it, and it looks like that, and then looks like this. Okay, so a lot of times the hole appears that it should have been a vertical asymptote. A hole has a higher order power than an asymptote, so that's why that takes place. Okay. The other problem I wanted to talk about was if we just had like this, so if we had x to the third on top, x to the fifth on bottom, this is where our horizontal asymptote would be y equals 0. Okay, and I'm not going to worry about graphing something like that. But then the last thing I want to teach you is, so the first problem is the degree on top was equal to the degree on bottom. That doesn't mean that you have a hole because of that. It's just because when I factored one of the binomials was the same on top and bottom. And then what you do is you just set that binomial equal to 0, plug in that x value into whatever you have left, and that gives you where the exact coordinates of the hole would be. Yeah.
What is a hole?
Let's do this. All right. Vaguely. So I'm going to graph this on Desmos. Okay, just so you can kind of see what it looks like. Desmos.com. Graphing calculator. Okay, so I had y equals, top was x squared. Was it plus 4x that I did? Plus 4, I think. All divided by x squared minus 4. Okay, so, oops. Okay, so this right here is actually our hole in the problem. And I'm just curious what this is going to look like. This is not going to show me my hole. I wonder if I zoom in a jillion times if this is going to look to be the hole. Not seeing the hole there. Okay, so let's get rid of that. Leave page. Go to my Graphing calculator. That one, maybe. Come on. 62 days left. I think we got time. Let's clear that out. So let's go y equals, whoa, y equals x squared, clear, parentheses, x squared plus 4x plus 4 divided by parentheses x squared minus 4. That 5 is not supposed to be there. Delete that. All right. So if we do a zoom 6, so that's what it looks like. But you can't, if I zoomed really closely in to right here, we would see a gap. And I'll show that in a sec, but I want to show you on the table. I said at -2. So you have 2 error. That's your vertical asymptote. And if I go up a little bit, I have the -2 is also an error. But at -2 and +2, at +2, you have this asymptote here. But at -2, that's an error as well. That tells you there's a hole, but there's not an asymptote there. So an asymptote will show up if it was on a graph as an error when you went to the table. But let's Z-box it. Okay, so at this -2, I'm going to put my cursor right here, and then we're going to zoom in, and this should happen eventually. And this is like, for you science folks, this is a we're going microscopic. It's supposed to, come on. Ah. Crap. Okay. Y equals graph. Zoom. Zoom standard. All right. I thought it was going to, on these old ones, quit out of there. Y equals there, zoom 6. If I wanted to calculate a value at -2, it tells us that we have an error. Okay, and the reason why it tells us we have an error is that hole does exist there. So the hole is literally a place that it doesn't exist on the graph. On the older calculators, it actually used to show the hole, and it looked like, as you zoomed in real close, it looked like this big old, like an EKG that's going up and down at the hole. But unfortunately, I guess TI felt that we couldn't do it anymore. So I guess the only way that we could see the hole on this is by seeing the -2. At -2, we know that there's not an asymptote. We have all these other values. So we're approaching the hole, get to the hole exactly at -2, it's a break in the graph. It doesn't act as an asymptote where an asymptote shoots up, straight up or down it, or shoots down it or shoots up it. So those are the places that you would see a hole. Okay. This one is just where you have the horizontal asymptote. Of course, you could have vertical asymptotes on this one. You could have holes. I don't know what the rest of the equation is. But the last thing I want to show you is something that looks like this. Okay, so let's say I had, oops, I don't want that. Undo. Let's say we had an equation like this. Let's say we had that. And then let's say we had bless you. So if I factored this one, because the degree on top is greater than the degree on bottom, this has something called a slant or an end behavior or an oblique asymptote. They all mean the same thing. They kind of will interchange those words. So the end behavior is as I go out to infinity, or if I go out to negative infinity that way, it's the graph. We could figure out the graph where it would follow along. So if we were to try and graph this one, that's fine. But if I went, and don't let this panic you, this is not going to be on the final. But if I wanted to find what the oblique asymptote would be, I'm going to use big old division. And let's do this. That'll work. All right, cool. Get out of there. Stop. All right, so I have 3 terms. So what do I have to multiply? I'm going to start this right here. If I multiply x squared times x, I'll get x to the third plus 4x squared plus 4x. If I subtract these, that cancels. That gives me negative 2x squared. And that gives me minus x. And then what do I multiply x squared by to get negative 2x? So I multiply by minus 2. So the line y equals x minus 2 is our end behavior asymptote. Yeah.
We use synthetic division as well.
Synthetic.
You just cancel out the number.
Synthetic kind of works, but this would have to be factored because you want a number there. You don't want a polynomial.
Well,
so that factors the x plus 2, so technically you could divide by negative 2.
So you will, because there's a way of doing that, I know.
Because synthetic division would have looked like this.
They use you can use like one of the numbers to like.
Yeah, so we would use negative 2 because this factors x plus 2. And then you got 1, 2, 3, and 0. And then you could use synthetic division. So let's just graph this on Desmos, and I want to show you what this end behavior will look like. I'm going to write this down now. So jump back to our friend Desmos. Not demon. So y equals parentheses x raised to the third plus 2x squared plus 3x divided by x squared plus 4x plus, oops, not equals. Plus 4. Okay, so this is what the graph looks like right now. Let's take that and make it better. So that's basically what the graph looks like. Okay, yeah, you have this asymptote that would exist at -2. So if I did x equals -2, there's that asymptote. But then on my thing, I forgot what it was, x minus 2. If I also graphed y equals x minus 2, and let's take this back out of this form. Let's do this. That green line, as I'm going forever this way or forever this way, so forever to the right or forever to the left, my graph goes along the slant, oblique, or end behavior asymptote, whatever they're going to use. So this is the line that we approach as we go to negative infinity, or we approach as we go to positive infinity. Okay? And friends, that's all I have for Algebra 2 content for you this year. So what I want to do is I want to give you the opportunity to go to Desmos. Okay. And I have to put this in our grade book. Let's see, groups, Algebra 2. So this is the review for what you will see on Monday. And you also do on Schoology. Capstone review. And rational functions. Add the course folder. We are in week 18, 10 to 14. This will make 10 points. Category, homework, scale, numeric, add. Okay, so if you log on to Schoology on your phone or on one of my Chromebooks or on your own computer, you can walk through this. You should get 100% on this, because if you try the problem and then if you needed to, you just watch the video. I just want to make sure I have this ready for you. Settings, enable, time limit, no. I'll let you attempt it 5 times. Randomized order, no. Using a review question, yes. Resumable, yes. Use submission, yes. All right, so if you go into the week 18 folder under My Cherry Creek, log in. Make sure I put it in the right spot. It'll show up. So if you go into the folder, oops, you go into this rational functions review. Oops, questions. So each problem will have a, let's see, it's like almost a 2-minute video, a 43-second video, 47-second video, 40-second video, a 30-second video, a 1.5-minute video, or a 1:50, excuse me, a 1:19, 48-second video, a 1:11 video, 56-minute video. So each of these answers, try the problem on your own first, and then answer the question. If you're not sure about the answer, watch the video, because the video will work the actual problem itself out. I believe I use Desmos on a lot of them, and Desmos is embedded and then also if you wanted to use your graphing calculator. So that's what I have for you today, my friends. So I'm going to stop my